So here are the ionic bonding problems that you should have been able to work through before yesterday's assessment. And why don't you take a moment, pause the video just to verify that they all look correct. I was able to have a Zoom session with a number of you guys to talk through these, and just notice every single ion that forms, whether it's sodium or oxide or bromide, they all have the same electron configuration as some noble gas has. Okay, so K plus has argon's electron configuration. 19 electrons and you lose one, now it's like 18 electrons, just like argon. So it's stable like argon. It has 8 valence electrons like argon has. Fluoride, when it gets one extra electron, it goes from 9 to 10 electrons like neon. So take a moment, make sure you have all of these correctly drawn out with how the electrons are being transferred, the number of atoms that you need for that to happen, and what noble gas each ion is similar to in terms of its electron configuration. It's identical to. And once you've looked over those, you can continue with the rest of the video. Okay, so let's move on and talk about covalent bonding. Okay, so this section right here just describes how covalent bond forms. So I'm going to zoom in a little bit and look at this diagram, and I want to talk through this a little bit. So the way to interpret this diagram, it's kind of like backwards. So you imagine the atoms that are about to form a bond start off pretty far apart. Okay, so if they're really, really far apart, there's not really an interaction between them. Okay, but as atoms start moving closer together, if a chemical bond is about to form, and that's called a covalent bond, what happens is that the energy of the system starts dropping. Just imagine if you had a little ball at the top of a hill, right? And if that ball was sort of right here and you gave it a little push this direction, boop, give it a little tap, you know what's going to happen, right? It's going to continue rolling down the hill all on its own. Okay? And eventually it would be down here. It might try to roll up the other side just a second, but it'll roll back down. Okay? And eventually it's going to settle here at the bottom. And something similar happens when covalent bonds form. But it's more like a jostling action between two springs. So if you imagine if there was, if atoms get close enough to one another, say if you're talking about a hydrogen atom and another hydrogen atom, if they're really, really far apart, maybe there's not a strong attraction. But if you can move these atoms, right, let me actually scoot these up a little bit closer to where I've identified. If you can move these atoms close to one another, a little bit closer, okay, and so maybe that hydrogen atom right there is my lasso select. Come on. Right? And so if that's not what I want it to do. If it moves kind of in closer, eventually it's sort of like there's a spring attached to them. Okay? And let's say that spring is kind of wound up a little bit. Okay? Okay, and so now these springs, I've got all sorts of crazy things happening now. Just get rid of those H's, okay? So let's say that there's some tension here, right? Now that they're close enough, this is like a chemical bond that's starting to form, and that spring is gonna be pulling in these atoms kind of closer to each other, okay? So then a moment later, now we still have those two atoms, but the spring is pulling them closer together, okay? Now, you know, some springs, if you push them in too far, they push back, right? So let's imagine these things get really close to one another, right? They're almost right on top of one another now. Maybe that's a little bit too close. And so, you know, we can imagine Maybe that's too close and the springs push back a little bit now. Okay, so there's probably a nice sweet spot somewhere in the middle where the spring is keeping these things connected. There's maybe some jostling back and forth, but if the atoms get too close to one another, they get pushed away, and if they're too far away from each other, they get pulled in. So like too far, it's getting pulled in, and too close, so being pushed away. Right? And then that scenario there in the middle is like sort of the Goldilocks scenario, right? Just right. Okay, so this is a little bit different than a ball rolling down the hill. Everything's gotten all messed up now. Okay, but it's the same type of thing. And that scientists say that the energy has been minimized here. Okay, so it's the same type of thing that is in this energy diagram here. And right here on the x-axis, this is like the distance between the atoms. And so I think this is for actually a bond between two hydrogen atoms. Apparently the ideal length is 74 picometers. That's the internuclear distance. So the distance between the nuclei. Between the nuclei, the internuclear distance, 74 picometers right there, okay? And so that would be like this scenario right here, with this distance being 74 picometers, all right? If it gets closer than that, it's like the ball going up the hill. It's not going to stay up the hill. It's going to fall back down to that ideal spot. So that ideal internuclear distance here, okay? And so that's sort of a nice visual in terms of the energy that's involved, okay? Now chemical bonds don't always form this way, but between two hydrogen atoms, they do. And so I've drawn a Lewis dot diagram for two hydrogen atoms. And I'm also, over here, I'm going to write out their orbital diagrams. 1s, and over here another one. And I'm just going to draw it backwards, just temporarily. Hope you don't mind that. Okay, so let's see what might happen if these atoms start approaching each other, okay? So this electron on this hydrogen atom, it's in the 1s orbital. I'm going to draw it right here, okay? But there is room for another electron in the 1s orbital. This hydrogen atom also has an electron in its 1s orbital, okay? But there's room for another electron in that same 1s orbital. I'm going to draw the orbitals around each atom, kind of like this, okay? And so let's imagine that this atom starts approaching in, and if it kind of moves in, now we've got two electrons, trying to get that hydrogen right there, two electrons being shared by the hydrogen atoms. Okay, in terms of the orbital diagram, you kind of have to think about maybe flipping this guy upside down or something. There's got to be a way I can do that. I have no idea how. Let's imagine that gets flipped upside down, all right? Because atoms don't really know up from down. But those atoms move in, and now we've got two electrons being shared in the 1s orbital of each atom, okay? So now each atom is kind of like a noble gas. Do you know which noble gas I'm talking about? This hydrogen atom, now it has an electron configuration of 1s2. And this hydrogen atom, now also has an electron configuration of 1s2. That's just like helium. And we know that helium atoms are very, very stable, right? Okay, so each hydrogen atom gets a stable electron configuration by sharing electrons. That's how a covalent bond forms. Okay, so I want to actually skip through most of this since we talked through that diagram, and now you've got this visual of a spring kind of pulling in the atoms or pushing away, and now making that connection with noble gas electron configurations. Let's go ahead and continue on right here. Okay, so covalent bonding normally happens when two or more nonmetals, when they share electrons. And you still end up with an octet of electrons. Okay, so, and don't worry about this at least part of the time business. Don't worry about that. Okay, so here's hydrogen's dot diagram. Here's chlorine's dot diagram. They just use X's instead of dots so we can keep track of whose electrons are whose. And when these things move in, you can see that the hydrogen atom now has 2 electrons, 2 valence electrons, and the chlorine atom has 8 valence electrons. Okay, so 8 valence electrons. Now, it's important to recognize that whenever you form a chemical bond in this way, it's when half-filled orbitals overlap. So in a covalent bond, they form when half-filled orbitals overlap. Okay, so if you think about the electron configurations of these atoms, right? Hydrogen has a half-filled 1s orbital, and it could accommodate another electron. And chlorine, it has a half-filled orbital as well. I just got to go a little bit further. 2p. 2p's are totally filled up. 3s is totally filled up. But in the chlorine atom, one of the 3p orbitals is half-filled. This one right here, at the end. Try to draw that a little bit more clearly. It got kind of messy there at the end. There, this one right here. Okay? So if this was an ionic bond, you could like transfer over the electron and get the octet that way. But then hydrogen would totally lose any type of resemblance to a noble gas, right? It needs an electron as well, right? Like if this electron got transferred over here, then hydrogen would have helium's electron configuration. Call that a duet. But what's going to happen then instead is that these atoms are going to share electrons. And so if I rewrite hydrogen right here, and I'm going to put it in red. Let me put this in red here. Okay, if I can rewrite that just right here, imagine that this atom kind of comes in and its electron could go right there, and maybe that's the 1s orbital on the hydrogen atom. Okay, well then the hydrogen atom would have a duet. Okay, boom. So now that's kind of weird to draw it that way. That's the hydrogen right there. It's the hydrogen atom and its orbital diagram kind of upside down. But so we don't have to worry about drawing it that way. We're going to use dot diagrams instead. So how does this happen with hydrogen? Here's the hydrogen atoms. And remember I mentioned yesterday, you don't actually have to put the dots starting on the top. You could just as easily have written them on the side. And then we imagine those two atoms move in. And now we end up with something like that. And these two electrons represent a covalent bond. Two shared electrons make a covalent bond. Okay, it's called a single bond. Okay, so we've got a single bond right here. In the next video, I'm going to show you how you can represent that by just drawing a line, and that represents the molecule as well. That's called its Lewis structure, but we'll see more of that in the next video. Okay. Fluorine. Okay, so of course fluorine has 7 valence electrons, kind of like that. We got 2 fluorine atoms. Please forgive me, it looks a little messy. Right? Each fluorine atom needs 1 more electron, right, to get an octet. So I'm going to redraw these where you have that half-filled orbital facing each other. Okay, and then we imagine them just sort of moving in, right? And now we've got something like this. And you know what, to make this even more clear, I should have been using different colors. That makes it very, very clear. All right, so let's go with blue, blue, and that was blue as well. Okay, so there you can see which electrons are coming from which atoms. I'll go with red and green this time down here. Come on. It's a struggle today, guys. Here we go. Pop. Lasso. Same thing. I definitely just clicked lasso. Come on. Right there. Green. Right here. That's a green one. And then finally, some of these electrons are coming from that fluorine. Okay, that's hopefully going to make it a little bit more clear about where the electrons are coming from. That one's supposed to be green right there. Boom. Okay, so that's a single bond. Should have just redrawn them. Just trying to be clever. There. Okay. Now, down here, I want to, maybe let's try number 6 on your own if you want to pause the video and give this a try. How does the water molecule get formed? I'll give you a hint. I'm going to show you the orbital diagram for oxygen. And notice that there are 2 half-filled orbitals right here and here. And remember, hydrogen has space as well in its 1s orbital for 1 more electron. Okay, so we could imagine that electron kind of getting shared here. And if you had a second hydrogen atom, its electron could get shared there. And look, then oxygen would have an octet of valence electrons, and each hydrogen would of course have one of oxygen's electrons. This electron, I've drawn it up here, and that one, I've drawn it over there. Okay, so what would the dot diagram look like? Okay, well, here's oxygen. It's got 6 electrons, and here's a hydrogen atom with its 1 electron, and I'll put the other hydrogen atom here. And we can imagine those atoms sort of moving in closer to one another. And now we've got a situation like this, where oxygen and hydrogen are bonded up together. Look at that. You can see that oxygen now has, what do you call 8 electrons? It's an octet. And each hydrogen atom, each one, has a duet. Hydrogen follows the duet rule, and all the other nonmetals follow the octet rule. Okay, so those are for single bonds. I want you to know about triple and double bonds as well. Okay, so if you have 2 oxygen atoms, and I'm going to line them up this way. Okay, well, we could get a single bond to form between them, right? But a single bond, turns out, is not going to be enough, because each oxygen atom needs 2 electrons more. So at this point, if you look at all of the electrons around each oxygen, it's only 7 electrons, okay? But what can happen is this electron here can pop in as well, and that electron can pop in as well. And now we'll have an octet of electrons around each atom. And this is called a double bond. Okay, so a double bond, look at that. I still have the same number of black electrons and blue electrons, but the ones in the middle are being shared by each atom. So there's 8 valence electrons for that atom and 8 valence electrons for that atom. So any of the ones that are in the middle are being shared. So a double bond has formed, and that's a real thing. Okay, so double bond, basically there's 4 shared electrons instead of just 2. Okay, and now finally I want you guys to know about triple bonds. Okay, so in a triple bond, so here's nitrogen, it needs 3 more electrons. And it turns out it can get 3 more electrons from another nitrogen atom. This nitrogen atom also needs 3 more electrons. So the first chemical bond that forms, imagine them moving into one another. All right, so they're just sharing from the direct overlap of those half-filled orbitals we talked about earlier. Okay, but now each atom only has 6 electrons if you kind of circle through and count them up. 1, 2, 3, 4, 5, 6. It's not enough. But we can imagine that electron and that electron get pulled in. So we're going to get a double bond to form. Okay. And so this one also now has a double bond that's formed. Okay. But that's still only 7 electrons. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. We're going to get 1 more electron from each nitrogen to kind of get moved in there, pulled in there. And that brings about the triple bond. So all right, so now between each atom, you've got 6 electrons being shared, and each atom actually still has an octet now. That's 8 electrons around each. Okay, so this is called a triple bond. Okay, 6 shared electrons. Okay, now drawing these dot diagrams can be kind of a hassle, and I mentioned a while back there's something called Lewis structures that are a lot easier to draw. instead of drawing all these dots. So a single bond is represented by just this line. So we can draw the fluorine molecule as a Lewis structure. Those two shared electrons I represent just with a line right there, okay? And we just fill in all the other electrons in the pairs that they're in on each atom. So that's the Lewis structure of the fluorine molecule. If you've got a double bond, each bond consists of two shared electrons. So if you have a double bond, that's 4 shared electrons. We just draw 2 lines. Okay, so there's the Lewis structure for the oxygen molecule. That's the fluorine molecule. Here's the oxygen molecule. It's a lot easier to draw, and there it's very, very clear you've got a double bond. And then in nitrogen, its Lewis structure has 3 lines attached. Okay, and we still keep those other pairs of electrons on each nitrogen. Okay, so that's its Lewis structure. Okay, so to finish up today's lesson, why don't you pause the video and attempt carbon dioxide? And here's a hint: there are 2 double bonds. 2 double bonds in carbon dioxide. Pause the video, give it a try, and then check your work here in a moment. Okay, so to finish up, carbon with 2 oxygens, right? Carbon and 2 oxygens. So I'll keep the oxygens as green. So here's my carbon. Carbon, here's its Lewis structure. And oxygen, moving it in, you could get a bond, right, from overlapping these ones here, and then we could also put a bond down on that one, right? Okay, so you get some overlapping electrons that way. Okay, so let's move them in. And so now we've got carbon with 2 electrons there, and oxygen. Oxygen here. Okay, but if you count it up, none of these atoms have an octet yet. That's 7 electrons around that oxygen. This is 6 electrons around that carbon, and that's 7 electrons around that oxygen. So none of the atoms have enough electrons yet. So we can fix this if each oxygen shares 1 more electron with the carbon, and if the carbon shares 1 electron with each oxygen. Okay, so drawing that in, what needs to happen is a little bit more sharing, some double bonds happening. So let's move some electrons in there, move that electron in here and down in there. And so the final structure is going to look something like this, just with the dots drawn out. Doesn't have to look exactly the way mine looks. All right, and normally we draw it straight, but notice we've got 2 double bonds on here. So the Lewis structure for carbon dioxide is like this. Okay, now it can be kind of complicated drawing these dot structures. I don't want you to have to worry about the dot structures so much. In the next video, I'm going to teach you a way to go directly to the Lewis structure. So instead of drawing a whole bunch of dots and trying to figure out how to move around the individual dots, there's a better method I want to teach you, but we will see single bonds like in the fluorine molecule, double bonds like in the oxygen molecule, and triple bonds like in the nitrogen molecule and the carbon, that's a double bond, excuse me. You'll see all those types, okay? So in terms of problems to attempt, there aren't any additional problems to attempt if you've already been pausing the video and going through the lesson as you should. So that's the end of this video.